Last time we looked at how the standard Gibbs energy is connected to the standard cell potential, but we really don't want to limit ourselves to just working at the standard conditions, because I think it's pretty obvious to see that most of the reactions that actually exist in reality are not at 1 molar and 1 bar for gases, only at 298 Kelvin. Besides which, the whole point of having standards is to enable us to explore the relationships between these thermodynamic constants at a wider range of thermodynamic conditions. If you recall from the thermo section, we could find the Gibbs energy outside of the standard conditions according to the relationship the change in Gibbs energy is equal to the change in Gibbs standard energy plus RT ln Q, where Q is the ratio of products to reactants outside of equilibrium. And since the standard Gibbs energy is related to the standard cell potential, then we can combine these equations to determine the cell potential that we should expect outside of standard conditions, which is the cell potential equals the standard cell potential plus RT over ZF times the natural logarithm of the concentration of the products divided by the concentration of the reactants. This relationship is called the Nernst equation, named after Walther Nernst, one of the people credited with founding modern physical chemistry. In addition to discovering the relationship between ion concentrations and cell potential, Nernst also developed the modern third law of thermodynamics, for which he was awarded the 1920 Nobel Prize in Chemistry. He established a research position that brought Einstein to Berlin. He was the rector of Berlin University and the president of 2 German national labs. Now, his own lab was stacked so high with books and papers that it was called the state of maximum entropy, which, if sometimes people judge you for being untidy, take this as a lesson that there's still hope. So where would the Nernst equation come in useful? Well, one of its implications is that 2 otherwise identical half cells at different ionic concentrations will produce a voltage when connected together. This opens up the opportunity for an early application to look at the concentration of an acid in a solution. Let's say that we want to create an electrical pH meter. If the potential of the hydrogen electrode is 0.0 volts at pH 0, then what voltage would we measure from the same electrode at pH 7.0, when it's all at 298 Kelvin? This is asking us to consider the potential difference between the standard hydrogen cell at 1 molar hydronium and another hydrogen cell where the concentration of hydronium is only 1 times 10 to the negative 7. We can write out these 2 half cells, but we have to be sure to write out the concentrations of each. Otherwise, you might be tempted to cross everything out from both sides of the equation. So when we go to calculate the value of Q, the ratio of products to reactants, we see that it's 1 molar squared over 1 times 10 to the negative 7 molar squared. And the Nernst equation tells us that the potential on the cell is equal to 0.0 volts minus 8.34 joules per mole Kelvin times 298 Kelvin divided by 2 moles of electrons times Faraday's constant, 96,485 coulombs per mole, all multiplied by the natural logarithm of 1 over 10 to the negative 7 squared. This means that the final cell potential is negative 0.414 volts. This means that the potential that we would read for a solution at pH 7 is negative 0.414 volts. So because the cell potential is negative, it tells us that the opposite reaction is the spontaneous one, which does stand to reason since the standard cell is such a higher concentration of acid than the cell at pH 7. But what it also does is gives us a measurable voltage that would stand as 1 point that we would add to a calibration curve that would allow us to build up an electronic voltage-based pH meter.